What's up guys, this is Angie from Algopedia, and in this video we are going to solve the smallest k integers problem, which is a coding interview challenge asked a lot of top companies like Google, Facebook, Amazon, and you got the idea. And it actually has a lot of different solutions. We are going to see each of those and actually go through the line of thought in which we get through some brute force solutions to some amazing ones. So let's get it started. First of all, the statement of the problem is short and concise, and it is. We are given an array full of integers and we have to find the smallest k integers. And I've prepared an example for you. In this input, as you can see, we are given an array. It has length 10 and all those integers, and we have to find the smallest 4 integers. And for that, let's search for the minimum, which is obviously 1. Then the next one is going to be 2. We have another 2 here, and we don't have any 2s, so there is going to be 3, right? So our answer is going to be 1, 2, 2, 3 in sorted order. But we don't have to do it necessarily in strictly ascending order or something like that. We can return these smallest k integers in whatever order we like. So if you return, let's say, an array that looks like this, and it is 2, then you have 3, then you have 1, and then you have again 2, this is completely fine, right? This is going to work too. And let's think about the most obvious solution ever. When you want to find the smallest k integers, it's pretty straightforward that you would like to have those values sorted already in increasingly order. But as the values in our array are not sorted, we are going to do that. So as we know, the complexity of sorting an array with size n is big O of n log n. So our solution is just going to sort our array and then with a for loop just take the first k integers. So this solution is going to have the time complexity of big O of n log n, right? Where n again is the size of our array. So big O of n log n is just the solution with sorting the array. So now the question arises, could we do any better? And we surely do, because in this solution we are sorting every element, and that's not so okay, because we only want the smallest k integers, right? So if I could find a way to only keep those increasingly sorted, it would be great. But remember, isn't there a data structure which can do this, which can hold a collection of elements, in our case integers, and keep them sorting in some way? And it is the binary search tree. We can have a binary search tree in which we have our smallest k integers. We will iterate through our array and for our current element, and if this element is smaller than the largest element in our binary search tree, we will remove that element from the binary search tree and insert our new element. But let me show you on an example. So we have again our array A, which consists of these 10 integers, our k equals 4, and initially our BST, binary search tree, is empty. Now, obviously for the first k elements of our array, we are just going to insert those, right, until the BST gets full. So, first step is value 5, we insert it in our BST. Then, the second position, here we have value 9, we insert 9 into our BST. Then, step 3, we have value 3, we insert 3 in our BST, and step 4, we have value 6, so we insert this 6 into our BST, okay? Remember, these elements are going to be increasingly or decreasingly sorted, whatever you want to see it, but we can access the maximum element, and that's what we want, because when this BST gets full, so it has k integers, let's see what happens. We will go to the next element, which is 2, and we shall see what is the greatest element in our BST, and it is this 9. Now, because 9 is greater than 2, we will remove the 9 and we will keep the 2, right? So let me erase the 9 here, and we will instead insert the 2. Now this is our new BST. Let's go to the next element, which is 1. Now, take the largest element here, which is this 6. 6 is greater than 1, so go ahead, remove the 6 from our BST, and instead, obviously, we will insert our 1. This is the new BST. Let's go to the next element, which is 3. The largest is 5, so we shall remove the 5 and insert the 3. Let's remove the 5 here. Perfect. And let's go on and insert this 3. Now this is our BST, 3, 2, 3, and 1. Next element is 2. Now the largest element here is 3, so we either delete this 3 or this 3. Let's take this one for example, doesn't really matter, and we will insert our 2. So let's insert our 2, and then for the next step we will have 7 and 5, which are both greater than our greatest element here, which is 3. In the end, obviously, our answer is going to consist of the elements in this BST. Now the question is, why is this solution better than the first one, which is big O of n log n? Well, as we know, the BST performs each operation in big O of log of the number of its elements. And how many elements are going to be in our BST? Well, obviously at most k. So each operation here is going to be performed in big O of log of k, right? And how many operations at max we perform here in our program? Well, let's think about it this way. For each element, right, we insert it into the BST maximum 1 times and remove it from the BST maximum 1 times, right? So having exactly n elements in this array and each element being inserted and removed maximum 1 times, that means we are going to have at most 2 crossed n operations. And each operation is now performed in big O of log k, which means that our total time complexity here is going to be big O of n log k, right? And because our k is less or equal than n, obviously, this would be a better complexity than this one, right? So this is our second solution. Now, of course, when k's value is super close to n's value, n log k and n log n are not going to be super noticeably different. But we can do something smart here. And when this k, let's say, is greater than n, our n divided by 2, we can flip the script of the problem. And instead of finding out the smallest k integers, we can find out the greatest k integers. And of course, this problem is going to be solved super similar to the first one, but in this case, we will take from the BST the smallest element, compare it to our current element, and if the current element is greater, we insert that in our BST. Now, as we said in the beginning, we don't need to return this solution vector sorted increasingly necessarily, right? We only should return the smallest k integers in any order that we want. So, you have probably thought about this. We don't need necessarily a BST. We can use something similar. And this something similar which don't keep them sorted, but we can always access the minimum or the maximum element. And for the smallest k integers problem, we will need the smallest one is going to be a heap, right? So instead of this BST, I can smoothly use here a max heap, right? Which again is going to provide me big O of log k per operation, and we are able to take the maximum value here, compare it to our current element, remove and insert. Perfect. Now, before getting to the optimal solution, I have a bonus follow-up just for you. Because you see, in coding interviews, a lot of times you are asked follow-ups after you provided the right solution. So for this one, imagine that our array A is constant. You are not allowed to change it, right? So, our first solution here would not have been accepted because we sort the array. And the second constraint is that you have big O of 1 extra memory. So you can't hold additional data structures like we used on the second solution, the BST or the max heap, right? So here we have again our array A, and I've written to the array A but sorted. Remember, we can't sort the array, but you will see why I did that. So, in order to have our smallest k integers, what I'm going to do here? Well, I want somehow to find what is the value of the smallest k integer, right? So, in this example, remember that our k is equal to 4. I want to see the value of the fourth smallest integer. And as you can see here in this example, it is going to be 3. And why is that? Because if I know its value, right? Let's just call it val. If I know val, I actually know all the smallest k integers. Because, let's take a look on our example. If I know that the fourth smallest integer is 3, obviously all the elements in this array which have a value less than 3 are going to be into our solution, right? So 2 is going to be 1 and this 2. And we will have some elements which are going to be equal to val. but not all of those, because if you can see in this example, we have 3 values which are equal to val. But if we take both of them, we would have 5 elements into our solution, but we only want 4. So all the elements less than val are going to be taken into our solution, right? Plus some elements, not all of those, but some elements which are equal to val. Now the question is, how many elements are here which are equal to val? How many am I going to take into my solution? Well, I need to know how many elements I have which are strictly less than val. And if we call this x, and our solution is going to have the smallest k integers, so length k, obviously in this set we will have k minus x elements. So if we find a way to know the value of the smallest k integer, not its position, just its value, we solve the problem. Because we will iterate through our array, we will take into our solution all the elements which are strictly less than val, and we will take into our solution k minus x elements equal to val, where x is the number of elements strictly less than val in our array. And how to find val? Well, we definitely have a brute force approach for this, because val is going to be a value from this array. So we can try out, why not, each value in the array. And for each value, we will perform another for loop to count how many elements are strictly less than val. Alright, and let's call this value x. We will make then another for loop to find out how many elements are less or equal to this val. And let's call this y. Right? Now, in order for this val to be valid, we know that our k should perfectly be between x and y. So if x is less or equal than k and k is less or equal than y, we found our desired value. So this solution is big O of n squared, right? We have a big O of n squared, but we can be smarter about it. And let's think again about this x and y. If we find this x and y, we shall compare our k to them. And let's say for some val, we found the x and y. If k is between them, alright, we found our answer. If not, there are only 2 possible cases. Either this k is less than x, or this k is greater than y, right? And let's think about this one. When k is less than x, how is going to be our actual value, our answer, compared to the value we just tried? Think about it. It's going to be smaller, right? So we will need a smaller val. Smaller val. Now, think about this case. When k is greater than y, we are going to need a greater val. So we are going to need here a greater val. And these 2 observations right here lead to the following idea. We can binary search the val. Instead of trying out each value in this array, we can just take the range, alright, starting at value 0 and ending at max val, let's say, where max val is the largest possible value in our array, and binary search the answer. And for each val, as we say, we fix the val, we take a for loop linear time to compute our desire x, our desire y, and we just do these comparisons. If k is between them, we found our solution. If not, we either search for a smaller val, which means the right pointer in the binary search is going to be equal to middle minus 1, and if k is greater than y, our solution is greater. So we will take the left pointer and move it to mid plus 1. So with this binary search, we will have now a solution of complexity big O of n, and from the binary search, we will have here a log of max val, right? So here is max val. And of course, log of max val is less than n, which means this is way better than the brute force approach.